Hello, geometry students, and welcome to lesson 10.6, part 1, surface area of prisms and cylinders. We're separating this lesson into two parts because we felt like it would just be way too much to try to combine into a single lesson to do surface area of prism, cylinders, cones, and pyramids all in one lesson. We're splitting that up into two parts. I think you'll see why here. So a lot of new terminology here that you're going to be seeing in this lesson. But let's start off by checking out some terminology as it refers to a prism. Like, what is a prism? What makes a prism a prism? So this part right here is called the base. It's one of two bases, and the bases are always parallel faces to each other. So we'll write that terminology down as well, or what a face is. We're getting into that here. But a base of a prism is going to be congruent faces in parallel planes. That is key. For something to be a prism, there has to be two bases that are parallel to each other in parallel planes. And then some other terminology here. I think it'd be best to just point to that and call that a base as well. So those are the two parallel faces of this, or these are two of the parallel faces in at least in parallel planes. I feel like I could be saying that better, but there are other parts that are parallel to this, but these other faces around this figure, it's not always top and bottom of the bases, but going around the bases, kind of connecting the two bases together, these are called lateral faces. So right here is one lateral face. And I'm a basketball player. I think of moving laterally. I would be playing defense. I'm moving side to side. So in a sense, there's a connection here around the sides of the prism, so to speak, are the lateral parts. So these are always going to be rectangular. The bases of a prism may or may not be rectangular, but the lateral faces are always rectangular. So these are rectangular faces that aren't the bases. Rectangular faces that aren't the bases. My daughter is learning how to rhyme. I wonder if she would have recognized that those words rhymed right there. And then right here, this red part, that would be the height of this prism. It's going to connect the two bases in a perpendicular way. And you could also call it the altitude, so I think I'll put that underneath there. And then this would be right here. This edge would be considered a lateral edge. It's the part where the lateral faces meet. It's a segment where the lateral faces meet. And so that's some terminology for those two. This down here, I'm going to use a capital B for this here and here. This is going to be my H. This figure is called a net, and it's as if I took this figure up here and unfolded it, like cut along all the edges and unfolded it. I would have this. If I would fold this back together, I could take this, fold it together to come back to something like that in a three-dimensional sense. So we are looking at some three-dimensional stuff for the first time here in our class that I can remember at least. So this is called a net for the hexagonal prism above. Hexagonal prism above. And then this, you're not going to see too many of these, but this is an oblique or slanted. And if you counted all the sides here, there's 8 sides. It's a little hard to tell back here, especially what the sides are looking like. But this would be an 8-sided or octagonal prism, but it's oblique or slanted. So this is an oblique or slanted octagonal prism. So you still have these two parallel parts. This one, I'm just going to draw a real rough sketch here. Like there's this part that you can't see back there, or that's hidden. That's the base, that's the other base to this. There should be 8 sides to this whole shape and 8 sides to this whole shape. Those are the parallel parts in that picture. And then looking at the next slide, now coming up with the formula for these things. So lateral area is going to be the area of the lateral faces. It's not going to include the bases. This is the lateral faces area. So the area of the lateral faces is what is known as the lateral area. So on this one, perhaps there's a lot of ways you can look at these rectangular prisms in terms of their bases. Typically, most students and people would say, hey, this is my top and bottom are the two bases. In this case, that definitely works because those are parallel faces to each other, and all the ones going around those two, all these other faces, are rectangular faces. That's part of the definition of a prism. But you could, in rectangular prisms, also call the left and the right the bases. You could even call the front and the back the bases, and it would still work. The formula would still apply. This would be your height here on this one, and while I'm doing that, I'm going to put that over here as well. The same thing will apply here. So surface area is going to be the area of all the faces. Oops. So that's going to include the bases. So if you think back to what we just did back here, I'm going to derive the formula from this idea. So I'm looking at this net again. I've really just copied and pasted that, made it a little bit bigger here. And so this is B, this is B, this is H here. To find a formula for just the lateral part, that would be all these rectangles right here. That would not include this base or this base. Likewise, for these rectangular prisms, if you made a net out of this, I'm just going to draw a quick sketch of what that might look like. It might be something like this. That is looking horrible. So you'd have a bunch of rectangles like this. That would be like, this part would be the front, this part would be the right side, this part would be the back side, this part would be the left side. And then you'd have the top and the bottom. So these would be your bases here and here for this one. If we were to look for the area of this lateral part, you could do height times whatever the side length is of one of those. So you could do side length times height, and then multiply that by 6. Over here you could do side length times height, and then these ones are actually different sizes, and that could happen here as well. These rectangles might not all be the same size. If this is not a regular hexagon, these would not all be the same size. But if you just took the perimeter of this base right here, or the perimeter of this base over here, it's all going to connect, if you fold it back up, to this right here. So right here is the same thing as the perimeter of the base from there to there. Likewise, from here to here is the same thing as the perimeter of either of these bases. So if we're talking from here to here, I could call that a capital P for perimeter. And to find the area of this whole lateral part, instead of doing each rectangle individually and adding them all up together after that, why not just do perimeter times the height? And that's the formula. So the lateral area, which you might see as just L, or you might see as LA, depends on the textbook you're using. The lateral area, I'll use just L, is perimeter times height. So that, I would circle that, highlight that. That's one of your two critical equations for right now in this lesson. This P is referring to, I would definitely make a note of this. This is the perimeter of the base. And this H is the height of the base. So the perimeter of the base and the height of the base. To find the surface area formula, remember we're including all faces in that, not just the lateral part. So we're going to include the bases. There's always going to be two in a prism, because that's the definition of a prism. If we go back to this, things that are prisms are like this. They're going to look like that. They're always going to have these bases that are congruent faces in parallel planes. We're including that here. So S or SA, depending on how your textbook might have it, the surface area is going to be the lateral area, which I'm calling L, plus the two bases put together. So plus 2 and then capital B. Capital B is representing or standing in place of the area of the base. So if we have two bases, they're always going to be congruent to each other in prisms. then you have just find the area of one of them and multiply it by 2. That's the slick, easy way to do that. So this is the lateral area right here. And then the B is standing for the area of the base, or the area of one base. And remember that 2 is coming from the fact that there's always going to be 2 bases in any prism. So what I'm looking for here in what I'm calling example 1 is just to label the bases. Look for those parallel parts. If it's a rectangular prism, they're going to be rectangles, the bases, but if it's not a rectangular prism, it's the non-rectangular parts. So look for the parallel parts that are the parallel faces that are in parallel planes. On this one, it would be kind of this triangle right here and this back triangle right here. These rectangular faces around it would be the lateral parts. On this one, you've got 1, 2, 3, 4, 5, 6, 7 sides. So you've got this heptagon base right there, and then there's the parallel part right there. All of these 7 rectangles around it are the lateral faces. On this, you've got that. You can't see the star underneath it. If you wanted to draw dotted lines under that to represent it, you could, but that would be a base that's showing there. For this hexagonal prism, those are your 2 bases. For this one, it's the 2 triangles here. And then this one, you've got your choice, or you have some options. Probably top and bottom is what most people would label it with. You could go left and right here, or you could go front and back as well. So this is the only one where you could use different bases besides the quote-unquote top and bottom for that. But let's take a look then, assuming that we've got this down. Looking at these now, let's use the formulas we just learned and plug in some numbers to find out what these values would be. So on example 2, part A, find the lateral area. It's just saying lateral area, not surface area. So we are going to exclude the bases. We aren't going to include those. For real life situations, there might be situations like that, maybe where you just want to paint the walls, but not the floor and the ceiling or something like that. How much paint do you need? Those are the kinds of application type problems that we want to be able to do after geometry in real life, whatever your job might be, to at least have that common knowledge base to be able to do some relatively simple problems like that, utilize what you're learning in a real life situation. So I'm going to use LA instead of L. I don't really care myself if you use LA for lateral area or just capital L for lateral area, but I'm going to do what I was doing before in previous lessons for chapter 10, show the formula in general first, and then plug in what I know and find what I don't know from there. So on this one, I've pre-labeled this one. I'm going to assume we're all going to consider the top and the bottom of the bases here. We've got 10 feet here, 3 feet here. We would also have another 10 feet here and another 3 feet here for the whole perimeter of this base. This down here would have the same perimeter. So for P, I'd be writing 3 plus 10 plus 3 plus 10. If you want to do that work off to the side and then just plug that number in directly to the formula, that's fine as well. I'm just going to do it in one place instead. And then the height of the prism, the height is always connecting the 2 bases in a perpendicular way. So 6 is the number, 6 is the value that's doing that. So from there, 3 plus 10 plus 3 plus 10 would be 26. So 26 times 6 should give us our answer. So this one would have a lateral area, not including the bases, of 156 feet squared. Don't forget your units. It's area, so we're multiplying feet. This is 26 feet times 6 feet. So it's feet times feet. That's where the feet squared comes from. Part B, on this one, we've got bases that are pentagons. So if this was a surface area problem, this would be a much more challenging problem because we would have to find the area of the base. And there's no, there is a formula for that, but you'd have to use some trig probably to be able to do that. This one's not even a regular pentagon, so that would be much more difficult than your typical prism problem might be. But this one, lateral area, is still same formula, perimeter times height. The perimeter of the base look up here, you've got 7, 8, 7, 8, and 8. They're already there for you, so there's no extra calculations that need to be done there. Just add those 5 numbers together, and then the height connecting the two bases is 11. So this is a pretty straightforward problem from there. No loops being thrown at you there. Are you throwing a loop at somebody? I don't think so. You're not being thrown for a loop. So 38 times 11, that is 418. No units are given, so you could leave it off, or you could write units squared. And then from there, let's take a look at example 3. We've got a couple parts for each one there. So find the surface area of the prisms below. We're taking a look at this as my base and this as my base. I'm going to assume it's top and bottom. You could do left and right. You could do front and back. You should get the same answer if you did it that way. So if you wanted to challenge yourself and try to do left and right or front and back and use that in your formula, let's see if you get the same answer. If you do that and you do it right, you should. So the surface area is going to be the lateral area plus 2 bases. So for the lateral area, I could change that to pH. That's what my formula was for lateral area, plus 2b. So that's another way you could write this formula. So if you wanted to even write this underneath here, if we go back to here, that's the alternate formula for surface area. Surface area is perimeter times height, that's lateral area, plus 2b. That's an alternate version of that formula. And so from there, let's see what we've got here. We've got perimeter is, we got a 4 and a 12 there. This would be another 4, this would be another 12. So you'd have 4 plus 12 plus 4 plus 12. If you did want to write 4 times 2 plus 12 times 2, not a problem. We've got that times the height. That would be 7.5 for the height connecting the two bases. And then plus 2b. So I'm kind of running out of space here. I'm just going to continue this thought down here. So I'm going to have, that's my pH part, plus 2 times b. My b in this case is base times height. This is a rectangle, so I'm going to use 12 times 4 for that. So this is right here. That's just base times height for the rectangle. Base times height. That's a dot, not a minus sign right there. So if we put all this together, 4 plus 12 plus 4 plus 12, that's going to be 16 plus 16, which is 32 times 7.5. And then here we have plus 2 times 48. And 32 times 7.5 is 240. And 2 times 48 is 96. Putting that together gives us 336. And no units given again on this one, so we could just say units squared or leave the units off depending on what your teacher's looking for. If you're one of my students, either way is fine. And then here, capital B, labeling my bases there and there. Those are my parallel planes, congruent bases and parallel planes right there. So on this one, surface area equals lateral area plus 2 times b. You can start like that, or you can write it like this. I don't really care if you jump right to this. That's almost preferable, or it may be preferable. I kind of think it is, that you go right to this if you haven't already calculated lateral area. If you're given that, then use this formula. But if you're not given what that is, then change lateral area to P times H and figure it out from there. So the perimeter of your base, it is not one of the rectangles. It's the parallel parts here. So on this one, we've got 4, 5, and you might know what this is already, but I'm just going to call it x for now, and we're going to solve for x. What could we use to solve for x? Looks like Pythagorean theorem. We know 2 out of 3 side lengths in a right triangle. So to figure that out, we could say x squared plus 4 squared equals 5 squared. That would be x squared plus 16 equals 25. That would be x squared. You subtract 16 from both sides, and you are left with 9. And then take the square root of both sides. That means x equals 3. So then from there, your perimeter would be 3 plus 4 plus 5 for the perimeter of the base. 3 plus 4 plus 5. Your height is connecting the two bases in a perpendicular way. That would be this length right here. That would be 11. And then plus 2 times the area of the base. That capital B is always standing for area of the base. That, in this case, is going to be a triangle. So you're thinking 1/2 base times height, hopefully, right here. That's where these values are coming from. So this is going to be 1/2 times the base and the height of the triangle, or the perpendicular parts of the triangle, the 4 and the 3 in this case. So 4 times 3 would be going in there. Then let's just simplify what we've got. So we've got 3 plus 4 plus 5. That's 12. 12 times 11 is going to be 132. And then this 1/2 times 4 times 3. Half of 4 is 2. 2 times 3 is 6. So you'd have 12 for 2 times 6. Put all that together and you've got 144 centimeters squared. So maybe this is that'd be kind of a strange tent, but maybe a building of some sort, and you need to have enough material to cover this whole thing. You would need 144 centimeters squared. That'd be a pretty small building. Maybe it's a building for ants. You could be calculating the surface area of a lot of different figures, triangular prisms. This is making me hungry right there. It's almost dinner time for my family over here. So my wife is actually making some pie for us tonight. How about that? I gotta stop looking at that. Let's take a look then at our final couple of slides for this lesson. So I put this in the same lesson, or we as a geometry team of teachers have decided to put this in the same lesson because it's really the same idea. Lateral area and surface area of a cylinder is the same as lateral area and surface area of a prism. Now, it might not look like it at first, but consider this as your base right here. This is like your capital B. There's 2 of those, so you could have a capital B up here as well. From here to here is going to be a radius, so I'll call that R, and then this is your height. So I'll do the same thing on this one. You've got a B and a B here and here. You've got a radius there. You've got your height here. So you have 2 bases that are congruent to each other in parallel planes, just like you do with a prism. I've got a net of a cylinder right here. So let's assume this net goes with these cylinders over here. Those are the bases, and then it's perimeter times height. But what is the perimeter of a circle? Because if you folded this back up and made a 3-dimensional shape out of it, this would line up with all of this. If you think of a soup can, if you think of a water bottle and you peel the label off of it, it makes a rectangle. So how long is this? Well, it's the perimeter, but the perimeter of a circle, we call that circumference, and circumference is 2 pi r. So from here to here is going to be 2 pi r. So the formula is exactly the same. It's lateral area equals perimeter times height, but perimeter gets replaced with circumference, which can be replaced with 2 pi r. So the lateral area, and I'll just call it LA from here on out. I think I'll be doing that more often. So if you want to go back to your original formulas and call this LA and SA, I think that's a good idea. But if you call it just L and S, not a problem. So LA is going to equal perimeter times height, which is circumference times height, which is 2 pi r times height. So most textbooks, that's the way you're going to see the final formula written out. This right here, this 2 pi r part is circumference, which is, circumference is just a fancy name for the perimeter of any circle. Circumference is just that. And then for surface area, you're going to be looking at lateral area once again, so the area of this rectangle plus the 2 bases. So this works, but then you can replace that with more specific information. Lateral area is 2 pi RH, and then the area, capital B, is standing for area of the base. Area of any circle would be, I hope you remember, is pi r squared. And so we've got 2 circles here. That's why it's 2 pi r squared. Right here, you've got 2 circular bases. And so from there, example 4, finding the lateral area of the cylinders below, we're just going to use this formula right here. LA is perimeter times height, which can be replaced with circumference times height, which can be replaced with 2 pi r times height. So if you plug in what you know, you can find out what you don't. You've got 2 pi times 4 is the radius, times 15 is the height. Multiply all that together, and then keep it in pi form at first. 2 times 15 would be 30, times 4 would be 120, so 120 pi. And then units is centimeters squared. This would be an exact answer in pi form. You may be required to know what that is. Take the time to plug that into a calculator. So pause the video for a moment, take out your calculator if you don't have it out, and type that in. Let's make sure you get the same thing as what I've got here. If I round this to the nearest tenth, those will be my verbal directions here. I got 377.0 centimeters squared. So exact answer right there, pi form. And then approximate answer, this one is rounded to the nearest tenth. On this one, I don't have a picture. You could draw a sketch if you found that helpful. But then it says D is 4.2. So that means if you divide by 2, the radius would be 2.1 feet. So then if we are just figuring out what's lateral area, not surface area, we're just doing 2 pi RH to figure that out. So we've got 2 times pi times 2.1 times 18.8. Now, a few of you that may have noticed this, hey, I'm dividing by 2, but then I'm just multiplying by 2 again. Yeah, if you wanted to use pi dh as your formula, I suppose you could. But I've never seen that written in a textbook like that. But it wouldn't be wrong. It would still be correct. So 2 times 2.1, 4.2. And then 4.2 times 18.8, I got 78.96 for that. And you still have that times pi. So this would be an exact answer right there. 78.96 is not rounded off. It's exactly that as a decimal times pi feet squared. And then we can take that and plug that into a calculator. This is rounded off to the nearest tenth. I got 248.1 feet squared to the nearest tenth for what the lateral area, just around it, not including the circular bases, would be for a cylinder like this. And then I believe we have our final slide here, finding the surface area of these cylinders below. So surface area, now we're going to use that formula right here. And I could write it like this, but I'm going to go straight to the more specific way to write it out here. So surface area, you may need to write a little bit smaller for these ones on this side. If you write as small as I am, you'll be in good shape if you've printed this out and are following along that way. So surface area is going to be 2 pi RH, and I'm still going to stick with this, that I'm writing it out in general and then plugging it in after that. I'm going to be consistent with that. But you could plug in the values right away into the formula if you choose to do so. So 2 pi times 100 times 500 plus 2 pi times 100 squared. So we can simplify this using PEMDAS to get what we have for a value there. So I'm multiplying all this together. This would be 50,000 times 2 for 100,000 pi for this part. And then 100 squared would be 10,000, and 2 times that would be 20,000. So I've got 20,000 pi for the two bases put together. So this is the lateral area part, this is the surface area part. Combined, that gives me 120,000 pi. And this is millimeters squared on this one. Rounded off, that is approximately 376,991.1 millimeters squared to that nearest tenth right there. And then from there, let's take a look at part B. On this one, we're told the diameter, so be careful that you're dividing that by 2, finding the radius from there. That is 5 right there, so 5 centimeters. And so from there, plug in some values into your formula. So we've got surface area is 2 pi RH plus 2 pi r squared. Pretty straightforward one here, I think, from here on out. So I've got 5 for the The radius, I've got 12 for the height, connecting my two circular bases, plus 2 pi times 5 squared. And that would give me, if I multiply all this together, 120 pi. If I multiply this together, 5 squared would be 25 times 2 would be 50. So I've got 50 pi. Putting that together gives me 170 pi. And that would be an exact answer in pi form. That would be centimeters squared for the units. Rounding that off times pi, which is a little more than 3. So we've got 534.1 centimeters squared for that. And then example 6, our final example for this lesson here. Make sure you're writing small enough again. If you write as small as I am, it should be good if you're one of my students and have printed out this set of note takers here. So surface area, once again, is, let me write, be consistent with how I've been doing it. So SA is going to be 2 pi RH plus 2 pi r squared. So you'll notice in this one it's asking for the radius, but it gives you the surface area. So the S, or the SA part, is 48 pi. So I'm going to replace that with 48 pi. The height is 10, so anywhere I see an H, I'm going to put in 10. And then anywhere I see an R, I'm going to leave it as an R. I'm going to solve for R. So I've got this as my next step. So it's paying off that I'm writing out the formula in general and then plugging in numbers from there. Makes it a lot easier to try to follow and be consistent and clear with your work that way. 2 times 10 is 20. You've got 20 pi r plus 2 pi r squared. And looking at this, taking it one step further, or thinking back actually to Algebra 1, if you have, pi is just a decimal number, remember, so this is just some decimal times r. This is like 6.28 and some change times r squared, and this is a decimal. So you have r squared, and a regular number piece. From Algebra 1, this is a factoring type problem. So you could see some factoring in some of your homework problems here. You may or may not see that depending on what's been assigned, but it is possible that you would see factoring showing up kind of organically, naturally in a problem like this. It's not a contrived problem where we kind of force factoring into the problem. It's a problem where factoring naturally comes up. This formula is derived, this 2 pi RH plus 2 pi r squared is derived the way you saw me go through it over here. And so this naturally is a place where factoring could be applied to figure out the answer to this. So if we subtract 48 pi from both sides, that's going to get me one side equal to 0. That's minus 48 pi on both sides. And then from there, I could take a 2. I could factor a 2 out of everything, and I could factor out a pi out of everything I see here. So I'm going to do that in the next step. I've got 0 then would equal 2 pi times r squared plus 10 minus 24. So now that I've factored out 2 pi, this should be a lot easier to deal with. I forgot to write an r in there. There we go. So r squared plus 10r minus 24. It's like, in a sense, I've divided each one of these terms by 2 pi. So when I'm factoring, it's like I'm doing that. I'm taking everything out of there, putting it on the outside, and then writing what's left after that division of that factor on the inside of the parentheses. So from there, you may remember something like this, where you're trying to find a product of the last number, negative 24, and a sum of this number. And if you're not sure, write out the factors of 24. So factors of 24, you'd have 1 and 24, you'd have 2 and 12, you'd have 3 and 8, and you'd have 4 and 6. 5 doesn't work, 6 is on the other side, so you've got them all from there. The ones that are possibilities that stand out to me would be 2 and 12 and 4 and 6, because you can either add or subtract numbers in such a way as to get 10 there, but we need a product of negative 24, so only one of these numbers can be negative, and the sum has to be positive. So that means that this is out, because if I make one of those negative, there's no way that those two numbers are going to add up to be 10. So if I do this one though, and I make this negative 2 times 12 is negative 24, but negative 2 plus 12 is positive 10. So then this becomes 0 equals 2 pi times, and I can use this, or these numbers are my factors. This is from Algebra 1, an Algebra 1 skill. I've got r minus 2 times r plus 12. Then looking at that, what would turn this whole equation into 0? What could I plug in for r? Well, r minus 2, if that became 0, the whole thing becomes 0. I've got 0 times everything else, still 0. So I would have here an option of positive 2, and here, to turn this factor into 0, that could become negative 12. But r is standing for something tangible. It's a radius. We're not going to have a negative length or a negative radius in Euclidean geometry. So I'm going to cross that one out. There's no negative lengths allowed in the Euclidean geometry that we do in this class. So you have 2 is your radius length, and this was in inches originally. So 2 inches, r equals 2 inches, that is your answer for this. You could take this and plug it back into here to check your work. I think that'd be a great idea. 2 times 2 would be 4, times 10 would be 40, so you'd have 40 pi, and then 2 times 2 squared would be 2 times 4, which would be 8 pi. So 40 pi plus 8 pi equals 48 pi. That checks out, that makes sense. And then finally, part B of this example 6. Let's write down the formula in general once again. We've got surface area is equal to the lateral area, which is 2 pi r(h) for cylinders, plus 2 pi r squared. And plug in what you know to find what you don't. Surface area is known, in this case, 320 pi. You've got 2 pi r times 12 plus 2 pi times, I'm almost putting r squared there. Hold the phone there, Mr. Wagner. So we've got 2 pi r, there we go, 2 pi r squared right there. I don't know what r is, so I'm trying to figure that out. So I've got 320 pi, it's 24 pi times r plus 2 pi r squared. So this is meant to be a very similar problem to what I just did before here. Here I just put the r squared part first, and then the r part, and then the regular number part, so to speak. I'm going to do the same thing over here. So I'm going to subtract 320 pi. I've got an r squared part and an r part, and so I'm going to get one side equal to 0 to allow for factoring to work. This would become 0 equals 2 pi r squared plus 24 pi r minus 320 pi. And like I did before, I'm going to divide everything in a sense by 2 pi. Factoring out the 2 pi is really what I'm doing here. But writing the divided by 2 pi sometimes helps students to see what to do next better. So taking out the 2 pi out of everything, factoring it out, I'm left with r squared plus 12r minus 160. So now you can do this same sort of thing. What multiplies to negative 160 but adds to positive 12? If I were to write out all the factors of positive 160, I'd have quite a few. So that 3 doesn't go into there, 4 would go into there. That'd be 15, 20, that'd be 40. And then we'd have 5 would work, 5 into there, 12, 20, 32. And then 6, I don't think is going to work. 7, no. 8, yes. 8 times 20. 9, no. 10, yes. 10 and 16. 11, no. 12, no, I don't believe so. 13, 14, 15, none of those work. And then 16 is already on the other side. So looking at this combination of factors, or this possibility with the factors, which one do you see something that could add or subtract to get a 12? The only thing I see here that could possibly work is this one. And we do need a negative product, but a positive sum. And so the way to make that happen would be to make this a negative. If I made the 20 a negative, then it's going to be a negative sum instead. So taking this, negative 8, positive 20, and multiplying those together, I get negative 160. Adding those together, I get positive 12. So then this could be rewritten as 0 equals 2 pi times r minus 8 and then r plus 20. If I FOILed this back out, r times r squared, this would be negative 8r and positive 20r, which is positive 12r, combining like terms, and then this is negative 160. So from there, I've got two options once again. This one could be 8, or this one could be negative 20, but we're going to cross that one out. Once again, no negative lengths or no negative radii. And so this would be h for r, and then that would be in feet, it looks like. So 8 feet is what my radius is for that problem. So we've got two factoring problems here. You may see that in the homework, you may not. Depends on which problems get assigned, but it shows up naturally, organically with surface area problems where factoring might apply if you're trying to find what the radius is for something. I hope you found that helpful. I know that was a little bit longer one than what is typical, but there's a lot to cover here. I can't imagine doing this plus prism or plus pyramids and cones all in one lesson. So I think it's good that we split it apart and did just prisms and cylinders for now. Hope you found that helpful. Feel free to comment and let me know if you saw any mistakes, or if you're one of my students, send me an email if you have any questions about it. Hope you're having a great day. Hope your rest of your day goes well, and I will catch you for the next lesson. Bye-bye.